This is lesson 4 of the quantum mechanics mini lecture series titled Black Body Radiation, sometimes abbreviated to BBR for short, black body radiation. Now, around the same time as scientists were looking at the spectra given off by different elements, as I talked about in a previous video, scientists were also studying the light given off by what's called a cavity, which is like a closed heated oven with a small hole. Okay, so let's draw a cavity. Here's the inside of it. And so if you heat up, so send in radiation, it'll just bounce across the walls and then bounce back out. Okay, this is called a cavity. Okay, it's a box of radiation. Now, by definition, a black body, BB, is a body that completely absorbs all electromagnetic radiation falling on it. Okay, inside the cavity, if you look here, radiation has nowhere to go. Okay, and it's continuously being absorbed and re-emitted by the walls. Okay, body which completely absorbs all EMR, electromagnetic radiation, falling on it. Okay, so it's continuously being absorbed by the walls. Here are the walls, continuously being absorbed and re-emitted. Now, the hotter and hotter you heat up the cavity, you will eventually reach what's called the visible part of the electromagnetic spectrum, the EM spectrum. Okay, visible means your eyes will be able to perceive it. You'll be able to see it. You'll be able to see it glow. Okay. Now, this was around the latter half of the 19th century. Okay, mainly in Europe, scientists in Europe, particularly in Germany, were studying cavities. Okay, ovens, pretty much. And it's worth noting that there's no such thing as a perfect, ideal black body. Okay. Something which completely absorbs all electromagnetic radiation falling on it, it's something that's not observable in everyday life. It's just not possible. Now, measurements actually showed that the intensity, okay, also known as the color in layman's terms, of the radiation varies very strongly with the frequency of radiation, so proportional to the frequency of radiation. What does that mean? This means proportional to. If I can spell it. Proportional to, okay? It's linked, it's related to, in other words. So intensity, the color, is related to frequency. What does that mean? Well, frequency, if you remember, back from junior school, if you don't, that's okay, is how many peaks, how many crests of a wave pass through a certain point in, specifically in 1 second. Okay, so let's say I'm standing here and I set my timer and I count how many peaks are flowing that pass by me. So I'm standing here. Hypothetically, there's a wave passing by. Set my timer and I stop counting at the end of 1 second. I'll see 1, 2, 3, 4, 5 peaks. Okay, so the frequency is 5 and the units for frequency is Hertz, H sub Z, named in honor of Heinrich Hertz, the German physicist who experimentally discovered radio waves in the 1800s, late 1800s. Okay, similarly, if there were like 10 peaks, let's say, 4, 5, 6, 7, 8, 9, 10, frequency will be 10 Hertz, right? So that's what it's saying. Color and frequency are related, right? If you adjust the frequency of the electromagnetic radiation, you see a different color. Okay, and high frequency typically is typically, let's say, gamma rays, X-rays, UV, ... Okay, it could correspond to one of those. Gamma rays are found in nuclear reactions, in dying stars, exploding stars in space. X-rays, we all know where they're used. No prizes for that one. Ultraviolet from the sun. And these are high frequency waves. Low frequency is like visible light. The light that we see coming up out of light bulbs from personal devices like phones, etc. So if you were to plot it, here's what you would see. Let's call this intensity, so the color, in other words, radiation. I'm not going to put numbers in, just going to keep it arbitrary. Frequency of radiation. You would see something like this. Okay, there'd be numbers here. And if you get these, let's say, these curves, one corresponds to a temperature, temp, let's call it X degrees Celsius, and the bottom one, Y degrees Celsius. This one will have a higher frequency than this one. Okay, temperature X than Y. Why? Because the peak is shifting towards the right, okay? Assuming that the frequency is increasing that way.